Yeah, you make scalloped potatoes.
Okay, so let me kind of go through the big picture on some of these problems. All right? So if you look on number 2, okay? So number 2, I take you through different stages of this. The first thing I'm going to say, okay, here's this beaker. We're going to add so many grams of acid and so many grams of sodium acetate. So right away, that's going to make this thing a buffered solution. And again, you have to visualize what's swimming around inside that beaker, okay? So you've got the acid itself swimming around, and you have the anions swimming around, okay? If you just, and this is going to be important in terms of the lab that you're going to do today, if all you had was acetic acid, no buffer, you hadn't had any sodium acetate, the only thing that would basically exist are those, is the molecular form of that anion, okay, or that acid. You'd have a tiny, 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 tiny number of anions floating around, but not very many at all. The vast majority of the fish in that ocean would be the molecular form of that. Okay, you'd see very, 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 very few of those. Now, as soon as you add the anions to it, then it becomes a buffered solution. So on 2A, you want to determine the initial pH of that buffered solution. Really, on 2A, have we added any hydroxide?
Nope.
No, no hydroxide. Okay, we're not titrating this. The only thing we're going to do is just going to have the base. We're just going to ionize. So this is just going to be your acid turning into your hydronium ions and your anions. Okay? That's it. There's no base. We're not neutralizing it. Nothing. So here's your rice chart. Now, you can work this a couple of ways. Ideally, you would work it in molarity. So, because if this number is wrong, then this entire problem is going to be wrong. So if you find the molarity of your acid, of that acetic acid, that should be 0.167 molar. That's your molarity, okay? That isn't the number of moles, that's the molarity. And that anion concentration, if you do that right, is going to be 0.0122, okay? Because if that's wrong, this whole problem is going to be a train wreck, okay? Again, that's your molarity. That isn't the number of moles, that's the molarity. Because if you take the grams, convert them into moles, and divide by 2 liters. Yes?
Did I do it wrong if I left it in moles?
It works out. You can do it that way.
Okay.
But technically, okay, this needs to be in molarity. Mainly because down here you're going to be dealing with the Ka value, or you're going to use that Henderson-Hasselbalch pH plus your pKa plus the log of your anions over. Technically, it has to be molarity. Okay, so that first answer on 1A should be around 4.6. Okay?
2A?
Huh?
2A?
2A. Should be around 4.6. Now, here's what's going to happen on B. Now, right, the net ionic equation reduction occurs, and now we're going to add sodium hydroxide to the solution. So again, you have to understand that you're going to have two things swimming around in here. You're going to have the acid, and you're going to have the anion. What's the hydroxide going to react with?
The acid.
Yes. So on B, your net ionic is the acid plus the hydroxide yielding anions plus water. Okay? There you go. So obviously you're adding a base. So your answer to 2C should be just a little bit bigger than your answer to 2A. Okay, still in the 4.6 range. Okay, still in that range. Now, when you get to E, now you're going to add hydronium ions. Don't worry about the chlorine, not part of the story. Okay, not important, not relevant. Chlorine ion is not going to do anything because it's stable. Okay? It's like the chlorine shows up at a party, it's not going to react with anything because it doesn't need anything. Chlorine ion is just chilled going, sup, you know, not going to interact. So, but what is going to happen is that hydronium ion is going to interact with the anion to reform the acid. So at this point you should realize, ooh, I'm going to be adding hydronium ions. That's probably going to make it more acidic. So your answer to 2E is going to be a little bit less than your answer to 2A. Okay, not a lot, but a little bit. So all of your answers, and this is an ish, all of the numeric answers on number 2 are around 4.6. Okay? Not a lot of variance on that. All of those answers are around 4.6. And again, like Eli said, on some of these, it's because you're dividing by the total volume. You can work in moles, you can work in millimoles, you can work molarity. I just beg of you, WWBD when it comes to the units. Okay? And I'm going to write down the units. I'm going to tell you that right now. Okay. Your answer to number 3 in the moles should be around 0.2. Okay? Should be around 0.2. On number 9, excuse me, not on number 9. On number 5, here's what's happening on number 5. You got nitric acid, strong acid, going to completely ionize. Okay? And then you're going to add the potassium hydroxide to that. So what you should see on number 5, your pH is going to, that first pH is going to start off around 1, and it's going to end up around 12. Okay? So on number 5, your range of pHs are going to be start from around 1 and end up around 12. Okay? And one of your answers should be 7.00 because it's completely neutralized, but it's a strong acid. You don't start a secondary reaction. Now, on number 6, notice when I type this up. On 5 and 6, they both are 50 milliliters. They're both 0.2 molar solution. But here's what's happening on number 6. 6 is a weak acid. 5 is a strong acid. Okay? So on number 6, those answers on number 6 should range somewhere between about 4 to about 10. Okay? That's an ish. But you should see that those pHs are growing progressively higher as you go from, as you progress number 6. They're going to start off at around 4. They're going to end up at around 10. Okay? Now, on number 7, 7 is identical to 6, except that now it's a buffered solution. Okay? So what you should see on number 7, because it's a buffered solution, and this is the whole point of buffered solutions, is that it mitigates changes in pH. So your answers to number 7 should see a much smaller range in pH than your answer to number 6 did. Okay? So all your pHs on number 7 should be between about 8 and 10. Okay? That's an ish. But it's going to be something around 8 and 10. Okay? All right. Now, when you get to number 9, hypochlorous, NaOCl, we're going to titrate this with hydrochloric acid. And again, what's happening if you compare 7 and 9? On 7, you have a buffered solution and you're adding a base. On 9, you have a buffered solution and you're adding an acid. So on number 9, that those answers on number 9 should range from, where's it at? Both of those should be around 8-ish, okay? 7 to 8. So those two pHs on number 9 should both be around between 7 and 8 on your pH scale, okay? On number 10, you're going to figure out what's going to happen with that pH. 2 of them should not change the pH. 2 of them should make the pH go up. 1 of them should make the pH go down. So on number 10, 2 don't change it, 2 make the pH go up, 2 make the pH, or 1 makes the pH go down. With that said, is there any specific ones that you would all want me to go over?
4A. That's me specifically.
And B.
Also 10.
Also
Some
10,
don't
yeah.
like that.
Okay. So first off, you got to have the terminology right. So on number 4, I'm talking about a strong monoprotic acid. Monoprotic just means it has 1 hydrogen, okay? So let's say that you have hydrochloric acid, quintessential monoprotic acid. Could be nitric acid, hydrobromic, whatever. Let's just call it HCl. And then we're going to titrate that against a weak monoprotic acid. Maybe that's acetic acid. Okay? So let's say that these are both 0.1 molar. And let's say that we have 100 milliliters of each. Okay? Start with the basic idea. Which one is going to fully ionize? The strong acid or the weak acid?
Strong acid.
Strong acid. So this is going to have a much higher concentration of hydronium ions. This is going to have a lower concentration of hydronium ions. So which one's going to start with a lower pH? The hydrochloric acid or the acetic acid?
The hydrochloric.
Because you have a higher concentration of hydronium ions. Cool with that. Now, when you get to 4B, quantity of base required to reach the equivalence point, okay? Equivalence point basically says, hey, the number of moles of my acid equals the number of moles of my base. So, even though this is a weak acid, when the hydroxide comes up, it says, give us a proton, okay? Mathematically, it's the exact same thing. For both of those, MaVa equals MvVb. And again, this is a cute little equation. It's wonderful, but understand what this means. This means that when you neutralize an acid, when you take the molarity times the volume, that the moles of my acid is equal to the moles of the base. Notice that I don't have 2 versions of this equation. I don't have a version of this for weak acids and a different version of this for strong acids. Okay? Doesn't make any difference. If I've got 5 moles of an acid, whether it's a strong acid or a weak acid, it's still going to take 5 moles of base to neutralize it. Okay? So the 2 quantities are the exact same because mathematically we can't differentiate them. We don't have a separate equation like this for weak acids, and then we have another one of this for strong acids. Okay? Doesn't make any difference. The moles has to be the same. The moles of the acid have to be the moles of the base. That's it. There's no variation on the theme. Okay? All right. Now, the kicker of this is when you get to C, at the equivalence point. And keep this in mind when you draw your graphs today, when you draw your pH curves. So, you're going to have, if you have a pH versus volume, if this is a strong acid, nitric acid, whatever it is, okay? That's good. If you go back to what Skippy said, we're going to start with a lower pH because we're going to have a higher concentration of hydronium ions, and that equivalence point is going to have a pH of exactly 7 because if you have hydrochloric acid, that Really? Thank you. That chlorine is not going to start a secondary reaction with water. Chlorine could care less. Chlorine's going, I'm showed up, hey, nothing's going to happen. However, you have that acetate anion. That acetate ion is going to go, whoa, 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 I'm a member of the Lonely Hearts Club. I'm missing my protons. So that anion on a weak acid is going to start that secondary reaction where that anion is going to react with the water. You're going to reform the acid. You're going to generate hydroxide ions, and the pH is going to go up. Okay? So mathematically, the moles are the moles, and you're going to neutralize it. But the reason that your equivalence point pH is higher is because of this secondary reaction. Okay? Cool with that. Got it. Good. Rand. What else did somebody want to go over? 10?
10.
I dissolve salt in water. The only way that you can alter the pH is if you change either the concentration of the hydronium ions or if you change the concentration of the hydroxide ions. Is sodium, and that's a cation, Na+, it's lost its electron. Do you think the sodium ion is going to react with water to form Na2+, because it's going to give up a proton, and H3O, which doesn't even make any sense, because because if the sodium gives up a proton, is it sodium anymore? No. So a cation of a single elemental cation is never going to react with the water. It's not going to happen because it's not going to give up a proton because it's bound together in the nucleus by the strong nuclear force. Now, what about chlorine? Is chlorine, oh God, I hate you today. Is chlorine going to go up to the water and go, give me your proton and reform hydrochloric acid and hydroxide ions? No. No. Even if it did, the hydroxide is going to go back to the hydrogen and go, hello, my dear, let's dance. And all you're going to do is just shift this thing back. Okay? It's not going to happen. Chlorine could care less about the water molecule. It's stable. It's happy. It's like, go away. I don't need you. So if the anion is the conjugate base off of a strong acid, nothing's going to happen. If the cation is an elemental sodium, potassium, lithium, something like that, nothing's going to happen. Okay? So sodium chloride will be no change in the pH. Now, in contrast to this, you have K2HPO4. Okay? So you want to look at the cation and then the HPO4 ion. Okay? Actually, that's 2 minus. Is the potassium going to do anything? God, no. Look at the HPO42. Is that the conjugate base off of a weak acid?
Yes.
Yes.
Yes. Yes.
Which one's that one? For chloric? No, it's not.
It's phosphoric.
Oh. Oh, yeah, it is. Sorry.
I thought you took this class.
I did. I don't remember all my acids.
I know. It's phosphoric acid. So this is why this is why you learn your strong acids, because if it's not a strong acid, it has to be a weak acid. So you look at that and go, wow, we haven't studied anything like that. Wow, that must be a weak acid. So you put this in water. Is it going to react with water?
Probably.
Yes, because it's the conjugate base off of a weak acid. What are you going to generate once it steals a proton from the water?
Hydroxide.
OH. What's that going to do to the pH?
Increase.
Make it go up because you're going to increase the concentration of your hydroxide
By
ion.
how much it goes up, or?
No, you can't quantify that if you had to. You don't have enough information. Okay? So the only thing you do is say it makes the pH go up. Just like I did yesterday with the demonstrations. Now, you get to the next one. This big molecular CH3, NH3, CO. Is the chloride ion going to do anything?
No.
No. Now look at this big monstrosity. Does it have an extra proton that it could give, an extra hydrogen, to give to the water?
6.
Yes. This does. Okay? This has some hydronium ions. So you can get, water comes up and says, yo, we have a proton. You know? Like the water standing there like on the road sign holding the sign. You know, like desperate for a hydrogen. This comes along and says, I got 6 of them. Okay, I don't care, I'll give you 1 of them. So if this gives up a hydrogen, if that gives up a hydrogen to the water molecule, what's going to happen to the concentration of your hydronium ions?
Up. Deep.
It's going to go up, so the pH is going to go
Down.
there you go. Okay? Makes sense. All right. Anything else?
Yes.
Lord.
6D.
On what?
6D.
What about it?
I got the wrong answer.
Well, I don't know what to tell you. Okay, so on 6D, Evan, did you realize that you completely neutralized the solution?
Yeah, and you end up with 10 millimoles of your anion.
Did you divide that by 150 milliliters to get the concentration of your anions?
Yes.
What did you get?
Wait. I got 2.22 times 10 to the negative 8.
What?
Wait, let me think about it. So I got 10 millimoles of the anion.
Yes, and the total volume?
How many different
That's-
words have you changed into today?
200. Wait.
You had 50 milliliters of the acid. You added 100 milliliters of the base.
150.
Yes.
Okay. .067. So that's my concentration out of,
Your anions,
yeah.
that's going to react with the water to reform the acid and hydroxide ions. So now it's acting as a base, so now you have to find that Kb value.
Okay.
Yeah. So this starts off at 0.06700 minus x plus x, all the drill. So Kb is going to equal x squared over 0.067.
Did you say photons or protons?
Find x, take the negative log of that, get your POH, and subtract that from 14. Okay, anything else? Going once. Going twice. So if you have that done, hit it in. If you need,
Yeah.
okay.
Oh, I forgot to say the square root of the answer.
So let me explain what's going to happen on how I wrote this lab. So you're going to do 3 different titrations. Okay. So the first titration you're going to do is just straight acetic acid. So you're just going to get 25 milliliters of a 0.1 molar solution of acetic acid. Okay? You know what the acetic, I'm telling you, it's a 0.1 molar solution. Okay? And you're going to titrate that with 0.1 molar sodium hydroxide, okay? So you're going to go through, now think this through. You have equal volumes, so you're going to have 25 milliliters of a 0.1 molar solution of acetic acid, okay? You're going to titrate that using 0.1 molar sodium hydroxide. So approximately how much sodium hydroxide are you going to need to reach the equivalence point? About 25. Okay? So what I would do, you're going to have in your beaker, use those volumetric pipettes, measure out exactly 25 milliliters of your acetic acid. You can use universal indicator or phenolphthalein, whatever you want to do. Put in the pH probe, okay? Measure the initial pH of just that, okay? There you go. Then you're going to begin to add your sodium hydroxide to it. I'd go like in 2 milliliter increments, like go maybe 2, 4, 6, 8, 10, 12, maybe up to 14. And then start going in 1 milliliter increments. Okay, you all know the drill at this point, not a big deal. You're going to generate that curve. So on your sheet, you're going to have 3 different columns. The first, where you've got like the dashed lines, that very first column is just going to be the titration information for just the straight acetic acid using sodium hydroxide. Again, rinse out your burettes with distilled water, rinse them with sodium hydroxide, run some of that out before you actually start the titration. You all know the drill. Now, the next thing that's going to happen. So, on that calculation 1, now you're going to start over. You're going to put in 25 milliliters of acetic acid. But then you are going to add 0.0, and I tell you exactly how much to add. You're going to add 0.0373 grams of sodium acetate into that beaker. So as soon as you add the sodium acetate, what does it become?
A buffer.
Now it becomes a buffered solution. Okay? So what you want to do down there on calculation 1, you're going to calculate the theoretical pH of that solution once you add that mass. Then I got bottles of sodium acetate in there. I've got the scales. Now, don't sit there and spend like 10 minutes trying to get exactly 0.0373, okay? As long as you're pretty close, okay? Because literally 1 granule on those sensitive scales might make the difference, okay? Just get something close, okay? Now, 0.4 is not close, okay? But this is why I've got those scales out there. Now, what you have to do, then on calculation number 2, what you're going to do is say, okay, hey, I want to start with a buffered solution of 6. Okay? That's what I'm going to start with. Now, with that one, here's what you want to do. You want to start with a buffered solution of 6. What you have to calculate is how much sodium acetate you have to add to 25 milliliters of acetic acid so that you start with a pH of 6. Okay? So what I would recommend on that second calculation, go pH equals pKa plus the log of your anions over the concentration of your acid. You know you want a pH to end up of 6. You can find the pKa of acetic acid, which by now some of you might have memorized is 4.74. You're going to know the concentration of your acid. It's still 0.1 molar solution. The only thing you don't know is the concentration of your anions. But remember, that concentration of the anions, when you get that number, is how many moles you would need in an entire liter. You're not making an entire liter. You're only making 25 milliliters of this. So when you get this, you need to do a couple of things. Roll the moles into grams, because the scales measure in grams, they don't measure in moles. Okay? And then figure out, wow, I don't need 1,000 milliliters, I only need 25. Okay? So on that calculation 2, let me give you a hint, and you can come up, and I want to check it before you actually do this, because if the mass is wrong, don't even do it, okay? But that mass on C2 would make a decent GPA, okay? Not stellar, but not bad, okay? So that will at least kind of tell you if you got that right before you come up and ask me. So I will tell you if your calculations are right for C1 and C2. No point going on if those are wrong. So we're going to start this lab today. Best case scenario, we get that first titration done. Then we'll do the second titration 2 and titration 3 tomorrow. Okay, let's go do science.